This video will be looking at inverse functions, the relationship between their domain and their range, between a function and its inverse, the relationship between their graphs, and then how to find inverses algebraically. Inverse functions are two functions such that the domain of the original function is the range of the inverse. This notation with the -1, it looks like an exponent of -1. We read that as f inverse of x. The range of the original function is the domain of f inverse of x. So the x and y values of these two functions are switching, and then those are the 2 points that we would graph to create the inverse function. A function has an inverse if and only if it passes the horizontal line test. Once we get into quadratic functions, we'll look at how we can not break that rule, but get around that rule just a little bit by limiting the domain. If you think about your vertical line test for a function, your pencil could never touch more than 1 point vertically. If we have a horizontal line test, we're doing the same thing, holding the pencil horizontally, and we would never want to touch more than 1 point on a graph of a function. The technical name for a function that also has an inverse are one-to-one functions. In a one-to-one function, no x value is going to have more than one y value, but we also are not going to see any y values repeated when we were to list out our domain of a function. So these two functions are inverses of each other, and you can go back and think about inverse functions meaning operations that undo each other: addition, subtraction, multiplication, division, square and square root, cubing and a cube root are all inverse operations of each other. So these functions are also inverses of each other. You would have seen that in your Desmos activity. You notice that your quadratic parabola flips over the line, and looks like it's a sideways parabola for a square root function. So also with this, we think about where these parent functions have shifted. So our parent function for the square root function has been shifted right 2 and up 1. Our quadratic inverse function has been shifted right 1 and up 2. So we see that we have the same values, the same numbers occurring, they're just in a different orientation. And then our domain for that square root function that shifts to the right, rather than starting at 0, now its domain is going to start at 2. And the range, rather than starting at 0, is going to start at 1. And the domain and the range of that parabola, so the vertex of that parabola, based on what we know about transformations, has shifted from 0, 0 to 1, 2. So the domain of that function would be 1 to infinity, and the range would be 2 to infinity. Now normally we think about a quadratic function having infinite domain, but if we're thinking about inverse functions and having to be 1 to 1, the result of that is we're only really going to graph half of the parabola. So the blue line is that half of the parabola that is the inverse function of the green square root function on that graph. So again, what we really want to focus on here is that the domain and range of those two values have shifted, and that's what causes this visual relationship between their inverses on the graph. Graphs of inverse functions: if the point xy lies on the graph of f, then the reversed order pair yx must lie on the graph of the inverse. So again, we talked about the domain and range, the x and the y switching places. The graph of the inverse is a reflection of the graph on the line y is equal to x. If you think back, or if you take a minute and go back to that previous screen with the quadratic in the square root, you could sketch in the line y equals x. The line y equals x is all those ordered pairs that are the same because y and x are the same numbers. So 0, 0, 1, 1, 2, 2. Same thing on the other side. So it would be right through the origin in the middle of that graph for that line. So if I were to graph a function and its inverse, such as g of x and the inverse, the blue line is our cubic function that has been shifted up 3 units. So normally our parent function has that intercept at 0, 0. It's been shifted up 3 units to 0, 3. The green line is the reflection of that. And again, you can see the point 3, 0 on the green line because we have shifted that point. So these 2 points are mirror images of each other. Also, the point at -1, 2 would be graphed at 2, -1. So they have that point marked for you on the graph. And there's 2 or 3 other points there that you can see. That to graph an inverse, if I can pick maybe 4 or 5 key points, flip the x and the y and graph them, we can see that reflection across that line y equals x in the middle. We're going to be finding inverse functions algebraically. And to do that, we're going to follow these 5 steps every time. Now, right now, we are not going to do step 5. We're going to leave step 5 for next week when we continue studying. Right now, we're going to just keep worrying about solving steps 1 through 4 until we get better at that skill. We're going to start on the right side. We're going to start by finding the inverse of f of x is equal to 2x plus 1. So we're finding a brand new function. So we're going to rewrite f of x as y. Those two things mean the same thing. Remember we said that the domain and the range switch, so we're going to physically switch the x and the y in the equation. So every place there's a y, it becomes an x. Everywhere there's an x, it becomes a y. And then we solve this equation for y. So we're going to isolate the variable. So we subtract 1 from both sides. So x minus y equals 2y. To get y by itself, we have to divide by 2. So we've solved that equation for y. There's nothing else to manipulate, so I found the inverse of that function f. For h of x, the first thing they ask us to do is to find the inverse. And I'm actually going to skip writing h of x. I'm going to go straight to writing this as y because I know that I'm going to have to rewrite that anyway. So there's my function. We're going to change all of the variables to the other variable. So now we have x is equal to the square root of y minus 2 minus 5. And we need to solve this equation for y. So the first thing we have to do is move the 5 over to the other side. I can't do anything with the radical until I have it isolated by itself. And then again, inverse operations. The inverse operation of the square root is to square the both sides, or square that, and I do that both sides because I have to follow the algebra rules. So on the left side, I have x plus 5 squared. On this side, the square and the square root have canceled, so I have y minus 2, so the last thing I need to do is add 2 to the other side to get y by itself, which is going to give me the inverse function of h. The last part of this question says to state the domain and range of h of x. The easiest way to do that is to think about the function h. That's a square root function. It's been shifted to the right 2 and down 5. So again, that changes where that point is starting. So the domain is no longer at 0, it's now going to be at 2, and it's going to go to infinity. The range is no longer at 0, it's been shifted down to -5. I just wrote my infinity symbol like it was an 8. infinity 8. So that's for the original function. If you're not comfortable enough with the transformations to be able to see and figure out domain and range from the equation, then graph it in Desmos, and you can always pull it from the graph. For the inverse function, all we have to do is take the domain and range for the original function and switch them, because that is our definition of inverse functions, that those two things would be reversed between the two functions. So again, graphs can be your friend on these. If some of those skills with graphs and transformations you're not able to visualize the domain and range. Again, we're going to dig into this rule more later, not right now. So if you see a question that asks you if a function is an inverse, we're going to use just solving for the inverse to do that. There will be other ways that we can verify later. We'll work on that in later lessons. So is g of x equal to x minus 8 over 5 the inverse of f of x? So the easiest way for us right now to show that is to take and follow those steps that we learned on the previous slide. So I take the function. We want to make f of x equal to y. We switch x and y. And then we solve for y. So we would add 8 to both sides. And then to isolate y, we would divide everything by 5. And so that is the inverse function for f, which is not what g is, because g says it's x minus 8. So the answer to this question would be that no, g of x is not the inverse of f of x. So you do need to be able to identify inverses with their graph, and you need to be able to find them algebraically and be comfortable with both of those things for this lesson.